All right, with all that background information, one of the things that you're going to be kind of responsible for is taking that information and interpreting what happens on a graph. So if we have a substance, again, let's just start with H2O. If it's at its lowest possible energy state, it's going to be a solid. Now, as we add heat to it, even though it's ice, we are going to get, ice can be at different temperatures. All right, so we're going to start interpreting this stuff on a graph a little bit. And so what we're going to do is, on the bottom part over here, this is kind of like time, but it's also about the adding of energy. So imagine we're putting something on the stovetop and heating it at a constant rate. So we're adding energy, which is taking time to do. And then on this part of the graph, this is a measure of our temperature. So what we would expect is if we took some ice and stuck it on the stovetop and we were able to record its temperature, is at some point, well, from the very beginning, its temperature would increase. And as you probably know, there's going to come a point when its temperature increases to the point that it's going to start melting. So we would expect the ice to melt. Now remember from a previous video, you can't have an increase in temperature and a phase change at the same time. Both of these things can't happen. It's one or the other. And so at this section we are having an increase in temperature. So when it starts to melt, what we're going to expect is there's not going to be a change in temperature. We're going to get a flat line here because a flat line on a graph indicates no change in something on the y-axis. So this is what would happen. So as it was continuing to melt, we get a flat line because there's no change in temperature. So during that time we have a phase change only. Well, once it is all melted, we've got liquid water, and the temperature is going to go up, 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 again because we can't get a phase change while the temperature is going up. And then at some point this is going to get to the boiling point and it's going to start boiling. And as we keep adding energy, we're going to continue getting a phase change. But remember, during a phase change we can't get a temperature change. And so only one can happen at a time. Notice again, the temperature, this line is flat, which means that the temperature is not changing. And then, assuming we could contain all this, because on the stovetop we can't contain it, but if we had an enclosed way to contain this, as we continued adding energy, the gas itself would then return to increasing its temperature, and the gas would get hotter and hotter and hotter and hotter. And pretty much for any substance we could have a graph that looks something like this. And so we can label these different parts. And what we want to pay attention to is think about what's going on at the flat part. So what we had going on here was melting. What we had going on here was boiling, which would be the evaporation process. Right? And then at each of these stages in between, think about what form of matter we had right here. So we had a solid at the beginning, which then melted and then turned into a liquid, which then boiled and then turned into a gas. And the other thing to keep in mind here is that means that during the melting time, that means there's a little bit of solid and a little bit of liquid. Both of them are going to be present. During the boiling and evaporation phase, there's a little bit of liquid and a little bit of gas. Because if you have some ice sitting around, it doesn't just go bam like that and all the solid turns into a liquid. It changes because each individual molecule is gaining its energy to be able to change into something. Okay, so this is our basic, what we call a phase change diagram. I keep using delta for change. Phase change diagram. And they're almost always going to have this shape. You're going to have something going up, flat, up, flat, up. And it's solid, melt, liquid, evaporate, gas. No matter which way, no matter if it's longer or taller, you're usually going to have these shapes to it. And each of these places is going to correspond to the terms that I've already got labeled on here. Okay. My last little thing to point out with this is, remember, this entire time we were adding energy to it. And remember from the last video is that if we're adding energy, then oftentimes the temperature is going to go up. And remember, if the temperature is going to go up, that means that we're increasing kinetic energy. Well, there's two places on this graph where we are adding energy, but this isn't happening. And that would be where the line is flat. So here and here, we're not getting this increase in energy, are we? Because the temperature is not going up. So in these flat lines, there's not an increase in temperature, which means that there's not an increase of kinetic energy. But we're still adding energy. So what's happening right here is that we're actually adding more potential energy. Okay, so because we're adding energy, we have to be adding either kinetic or potential, or both. But again, if we're adding kinetic energy, then we're going to expect a temperature change to go along with that. And so what's happening is that these molecules are just having a little bit more energy stored up into them. And then once everything turns into the liquid state, then the addition of energy will resume adding kinetic energy to it. All right, so can it go the other way? Yeah, we can have a phase change diagram that goes in the opposite direction because, again, in this case, we've got if we had a temperature over time, and again, this wouldn't be an adding of energy, this would actually be a subtraction of energy. We could have something that went down, over, down, over, and down. And so let's think about what's going on. This thing is cooling off, so over time its temperature is going down. That means that this top part is still the top part. So just like we had before, we went from solid to liquid to gas. Well, in this way, we've switched the graph around to show what would happen if something's cooling off. So this part then would be the gas, this part would be the liquid, and this part would be the solid. So we got a solid down here, we've got a liquid, and then we've got a gas on the top part. Just like we did on the other graph, it's just that it's turned in a different direction because the first graph was heating something up. This will be going in reverse and cooling something down. And then that would mean that these flat lines, again, our temperatures aren't changing at this point. And these would indicate the flat parts is the phase change. So we've got a gas turning into a liquid. When we went the other way, when a liquid turned into gas, this was evaporation, but now it's gas turning into a liquid. This is condensation. And previously we had a solid turning into a liquid, which means it's melting. This time we've got a liquid turning into a solid. When we do that, we call it freezing. Okay. So we can have a phase change diagram go up, we can have a phase change diagram go down. But here's your key over here is to think about the temperature. And remember, if the line is going down, that means the temperature is going down. If the line is going up, the temperature is going up. If the line is flat, then that means the temperature is not changing, and we're likely getting a phase change of some type. So if we had a graph labeled like this, we could hopefully determine a number of things about the substance and about the object. Again, by labeling all these things, we should kind of get an idea of what's going on. We got up, over, up, over, up. So this is our temperature is on the y-axis. So again, this is our hottest and this is our coldest. So A is going to be our solid. C is when it's purely liquid. E is when it's all gas. So B is going to be a combination of solid and liquid. And if we've got solid turning into liquid, then this is melting. D is going to be a combination of liquid and gas, which means that we've got evaporation. A couple of other things we can figure out from this graph is what is the melting point and what is the boiling point. Because the melting point is the temperature at which it melts, the boiling point is the temperature at which it boils. And let's think about this. This flat line is when it is melting, so for us to figure out the melting point, we just need to go to this side and look at the number where that is happening. So the melting point in this is 0. The boiling point, the same thing. This flat line is while it's boiling, so we just need to say what temperature is this occurring at, and this temperature is occurring at 100 degrees. So the boiling point would be 100 degrees. Also remember, the melting point is going to be the same as the freezing point, and the boiling point would be the same as the condensation point, because if we did this graph backwards, these flat lines would still occur at the same place. Okay, very last thing would be if we had two lines that were graphed on here and wanted to compare some things about it. So if we had two graphs on here, we should be able to compare the melting points of each. We should be able to compare the boiling points of each. And again, remember, the melting point is going to be our first flat line. We've already found out from the first graph that the melting point was 0. Well, what about the second one? Well, the second one, again, it would be, we want to look at where its flat line is. So this is going to be the solid part going up, and then this would be the point at which it was melting. So the melting point of the second one would be 20. All right, the boiling point of the first one was this line. So the boiling point of number 1 was 100. All right, and so the boiling point of number 2 would be this flat line, which would correspond to about 60. So if we wanted to compare melting points and boiling points, these would be the melting points of each one, because these are our first flat line. These would be the boiling points of each one, because that's our uppermost flat line. So in the red line, still everything would be, we would still expect the same. This first slope is the solid, the second slope is the liquid, and this third slope is the gas. And so then that means that this slope is when the liquid is turning into a gas, which is a boiling or evaporating. And then this line is when the solid is turning into a liquid, which is melting. And then the very last thing we could do with a graph like this is we could get an idea of which one has a greater or less specific heat capacity. All right, because remember our graph the other day had to do with the slope of the line. And so if we compared these two, actually I'm going to pause this and give you another line that's a lot easier to see. So I've put another line on here so that we can compare section C with both of them. So the red line would be, this would be when the liquid is heating up, and the dark line would be when a separate liquid is heating up. So we can look at the slopes of these, and what we can see is that the rate of change, this one is increasing faster, and then the red line is increasing slower. And so remember, if it has a flatter line, if it's increasing slower, that means that it has a high heat capacity. It's slow to fill up, kind of like the large stadium would be. If this one's filling up faster, that means that it would have a lower heat capacity. Its temperature is changing much more quickly. And so tying that back into the things we had last week, what we try to remember is if the heat capacity is increased, that usually corresponds to a slower rate of heating and cooling. So at least in the liquid phase of this, we could say that the red line probably has a higher heat capacity than the dark line, because it is changing its temperature at a lower rate. And again, the slope has to do with the rate. If it's flat, it means there's no change. And if it's close to flat, that means it's barely changing.